nanohub.org.
Online simulation and more for nanotechnology.
So finally today we're going to be able to do a little bit of uncertainty propagation, and we're going to put to use the polynomial, the orthogonal polynomials that we have constructed. Alright, so everything will pay off. So I'll just go over the quadrature rules really quickly, remind you what we talked about last time, and then we're just going to use the rules to propagate uncertainties through dynamical systems in two ways. One of them, we're going to call it the intrusive. It's going to give rise to the so-called intrusive polynomial chaos methods. Polynomial chaos methods that require you to write a new solver for a new dynamical system that propagates the uncertainties automatically. And then we're going to also talk about the so-called stochastic collocation methods that enable you to propagate uncertainty using polynomials, but without re-implementing your solver. You can just reuse whatever solver you have. Alright, so quadrature rules, quick reminder, we talked about the Gaussian quadrature that basically just takes a bunch of nodes on the line, let's say, and these nodes are the roots of a polynomial of degree n, and then this particular rule, it picks these nodes and then it uses the Lagrange polynomial to interpolate the function values on these nodes, and it has two properties. First, it interpolates exactly polynomials of degree 2n plus 1, which is remarkable, and it is optimal in the sense that there is no other rule with n nodes that can do that, but you should not really use it. And the main drawback is that, one of the main drawbacks is that it is not nested. Okay, so if you go from n to 2n, you're going to get completely different nodes, and you're going to have to evaluate your function at 2n completely new points, and you're going to completely waste your function evaluations, the function evaluations that you had before. So we're really interested in the most useful quadrature rules are quadrature rules that are nested, because they allow you to reuse whatever function evaluations you have done before. And the Clenshaw-Curtis quadrature is one of the most important nested quadrature rules, and it's not really important how it works, because all you're really interested in is just grabbing the nodes and the weights from some code. You should not really worry too much about where it comes from. You just know that it satisfies two things. First, it is nested. If you go from n nodes to 2n nodes, you are actually reusing your first n nodes. Okay, you just add n more. And it integrates exactly polynomials up to degree n plus 1. Alright, and this is what you should be using. And this is how it looks like, blah blah blah, whatever. Alright, so the CC rule is basically a rule that works in when you integrate things from -1 to 1 with a weight function that is basically equal to 1. So whenever you want to approximate an expectation, to estimate an expectation, you need to transform this integral to an integral between -1 and 1, and you can do that in any way you like. Okay, any function that will take x, which is from -infinity to +infinity to -1 to 1, would work. Okay, but I suggest that you use this. I suggest that you use the inverse CDF of the probability density of the random variable x, if you have it. If you don't have it, then maybe you should just do something else. Anyway, but the bottom line is that it's just a transformation of the integrand. And then once you have a nested quadrature rule in one dimension, you can construct nested quadrature rules in higher dimensions. The tensor product is the most obvious way to do that, but do not use it because it just explodes extremely fast. If you want to go to more than, if you have a something that is higher than a triple integral, it's not going to work. It's going, the number of function values you're going to have to do will be ridiculously high. So don't use it. Use the sparse grid quadrature rule or the small diag quadrature rule. There was a typo here in the formula. I fixed it, even though, again, if we wanted to understand what this formula means, we have to spend like a week on it, which is we're not going to do, okay? There are codes out there that can give you the sparse grids, the sparse grid of a given dimension at different levels, and the level of the sparse grid is basically controlling how many nodes it has. Okay, so the higher the level, the more nodes it has. And sparse grids are of different levels in 2 dimensions look like this. They look like the tensor quadrature without a lot of points, basically. Okay, so level 3, level 4, level 5, level 6. These regions may look empty, but if you go to sufficiently high level, they will start filling with points, okay? But you have to go to level 10 or so to see stuff in there. Anyway, and the reason why sparse grids are more useful than tensor products is because the number of nodes in them grows slower as the dimensionality increases, and this is how it grows. So you see that the tensor product explodes, whereas the sparse grid grows slower. But at the same time, sparse grids do not work all the time. Sometimes you can fool them, right? So if you stop at a specific level, there's always a function that can fool a sparse grid, right? So if you look at the sparse grid quadrature, let's say you stopped at level 6, if your function does something here, you're not gonna see it, okay? Does that make sense? If it has like a small bump here, you're not gonna see it. But anyway, that's just life, okay? Sometimes things don't work. Or most of the time things don't work. Sometimes they do work. Okay, so now that we have the quadrature rules, let's go ahead and propagate uncertainties. So we're gonna have to write a little bit because I don't see any other way I can actually explain to you how this thing works. All right, so what we wanna do is use the idea of polynomial chaos or polynomials, orthogonal polynomials, to propagate uncertainties through this dynamical system. So this is a differential equation, y dot equals something, and the y dot here is minus x 1 times y, so it's basically an exponential decay problem. We add, so one uncertain parameter is basically the rate of decay, okay? And another uncertain parameter is where you start the differential equation. So the initial conditions, 2 kinds of uncertainties. And we're gonna take both of them to be Gaussian, but of course, because we want this to be a positive number, the mean of that particular component is going to be very far away from 0, so that it is very unlikely that it is negative, okay? Because then it would be exponential growth. All right, so the mu corresponding to x1 is very far away from 0, and also the mu and the sigma is sufficiently small so that you don't go to negative values. And the same thing goes for x2. It should be a positive number because, you know, you have like a population of something that is dying. All right? So when we say that we want to do uncertainty propagation, what do we mean? We want to take the uncertainty in these 2 parameters and propagate it through the solution of the dynamical system. So we want to talk about the statistics of y induced by the uncertain inputs. Like, what is the expected y? What is the variance of y? What is the probability that y becomes greater than a given value at time t, or becomes smaller than a given value at time t? What is the probability that the half-life is this much? Whatever depends on x. Okay? Does that make sense? Do we all understand what we want to do? So let me just write it down. I'm going to delete it. So let's take as ytx. Say that this is the solution of the dynamical system, right? When the parameters are x, okay? So let's just write this like this. The solution of the dynamical system when x is x, where x is all the parameters, a vector containing all the parameters. So the things that we would like to compute are these. First, we would like to compute, for example, the expectation of y over x, right? So what do we mean by that? Well, take the solution and integrate over x. Okay, whatever x is, integrate over. Take the solution of the dynamical system and integrate over x. Fine, that's one thing we would like to find. Another thing that we would like to find, which is a measure of the uncertainty, of our uncertainty about the solution of the dynamical system, is these things, the variance, which is basically the expectation of ytx minus the expectation of ytx squared. Okay, this is the definition of the variance, which of course is just an integral, and it is this integral, ytx minus this thing, which is just a function of t squared px dx. And so on, you know, any statistic that depends on y, you can actually write it down as an expectation. Okay, so this is the kind of stuff that we want to be able to do. Make sense? And of course, you can do this kind of stuff with Monte Carlo, right? How can you get this, do this integral with Monte Carlo? You sample x's, you solve the dynamical system, you look at it at different times, you take the sampling average. You can estimate in the same way this thing, okay, the variance. This is what your the current homework is all about, okay? And you could also do it a little bit faster with Latin hypercubes, okay? Now we're going to develop a technique that does it without sampling, that basically defines another dynamical system that can just give you this right away, okay? This is what we're gonna do. Of course, there is a catch. The catch is that this only works for problems in which x is like 3, 4, 5, maximum 10 dimensions. Okay, because after that, the curse of dimensionality is going to kill you. And then the only thing you can do is Monte Carlo. But anyway, a lot of problems have 2, 3, 4, 5, 6 dimensions. Or, you know, because you're engineers, you can make them have, most of you at least, you can just make them have 5 dimensions by just simplifying the hell out of them. Yes?
The curse of dimensionality here is just in the integral, right?
Yeah.
So even the sparse grid method is not going to help us solve it beyond 4.
No. But it may be over 4. It may work for 4. It may also work, sparse grids may also work for like 50. If the function is smooth, they're going to work. If your function does crazy things as x changes, like if it has a discontinuity, for example, or a kink, sparse grids don't work. Okay? And in most interesting systems, this thing happens. You have a dynamical system that may pass through bifurcation points as you change x, for example, and might kick you from one equilibrium to another. Okay? In a discontinuous way. But anyway, here's the idea, all right? Here's the idea. It's very simple. Construct the orthogonal. So the first thing you do, step number 1, is you construct orthogonal polynomials, phi1 of x, phi2 of x, etc. And just pick n of them, okay? Orthogonal polynomials with respect to the density, probability density of x, using orthpol and all this stuff. So, with respect to x, or the probability density of x. So we have the polynomials, we have constructed them, fine. The second thing we do is we expand the solution at time t as follows. In this polynomial basis, basically. So we say y of t, if all the random parameters are x, I'm going to expand it in a polynomial basis. Okay, so here are my polynomial coefficients, here are my polynomials. The polynomials are functions of x, okay? And I better make the coefficients functions of t. So the coefficients change with time. You have a different set of coefficients at every time, okay? Make sense? Is this understood? All right. So what we're going to do now, so basically we have now casted the problem as the problem of finding this function to the problem of finding these functions, because we already have these functions. So what we're going to do basically is we're going to plug this in the differential equation and derive a differential equation for the coefficients. All right? This is the idea. So you just take the derivative of that with respect to time. The derivative is going to go inside the summation, and it's going to result in the derivative with respect to time of this. And you plug that into the equation and you get whatever you get. Okay? So let's call this equation number 1. Let's call this equation number 2. And let's start doing it. So let me do it on the next page. So the first thing I do is I take the derivative with respect to time. So let's say that this means dy dt. This is going to be dy dt of the sum I equals 1 to n ci phi ix. The ddt is going to go inside, and we can now write dci dt phi I of x, right? And that will be just writing ci and ci dot phi ix. Fine. No big deal. All right, but according to the equation that I have here, right, equation number 1, y dot is what? Y dot is minus x1 y. Okay? So y dot is basically minus x1 sigma I equals 1 to n ci phi ix. Okay? All right, so let me just write it a little bit better. It's gonna be, well, just leave it like that. Fine. All right, so what do I get from this? Now I get that sum I equals 1 to n ci dot phi ix equals minus x1 sum I equals 1 to n ci phi ix. This is the equation I get. And this holds for all x. And now I want to get an equation that will only have the ci's in it. What do I do? Any ideas? It's a function of x and a function of x. They involve the orthogonal polynomials. The polynomials are orthogonal, right? Take the dot product. Okay, with phi j. Exactly. You see it. So, what you do is you multiply with a phi j of x, okay, and you integrate over whatever you over the probability density of x. Okay. So when you do that, you're gonna get, the integral is gonna go inside, so you're gonna get this ci dot integral phi I of x, phi j of x, px dx, and this is gonna be equal to minus sum I equals 1 to n ci integral x1 phi I of x, phi j of x, px dx. Okay? Or in our other notation, we have ci from 1 to n, ci dot from 1 to n, like this. Here we have the inner product of phi I with phi j. Nice, we like that. And here we have minus sigma I equals 1 to n ci. And here we have the inner product of x1 phi I, which is just a function, right, of x, with phi j. This is it. All right. Now we're very lucky because this thing is delta ij, right? It is only 1 if I is equal to j, otherwise it is 0. So this is delta ij. right? So the whole thing is gonna just be sigma j dot on the left-hand side. And on the right-hand side, well, you just have this, okay? You have this dot product. So on the left-hand side, let's just write this dot product as follows. Let's just write Ci, let's call this Aij, okay? Where Aij is this dot product. And this dot product, well, you're gonna have to do it, okay? You're gonna have to do this dot product somehow, all right? So how do you think you do this dot product? With a quadrature rule, okay? So you pick your favorite quadrature rule, which consists of a bunch of weights, Wi, Wk, let's call them Wk, and a bunch of nodes, let's call them Xk, and you just do it. So you say that this is approximately, let's sum k from 1 to, I don't know, number of quadrature points, Wk, and then here you have xk1, phi I xk, phi j xk. Make sense? So now this is just a bunch of numbers that you can just calculate with a quadrature rule. And if you have this bunch of numbers, then the polynomial coefficient should satisfy this dynamical system. So let's just write it down here.
The left hand side should be sigma summation of the Ci, the del ij.
This? Yes, sum over I.
The left hand side.
No, this becomes only this thing.
Yeah, it is 1 or 0.
Yeah, so it's just gonna pick the j component.
Okay.
Make sense?
So you are doing component.
Yeah, you're just you're summing over everything here over I, and you only see j is going to survive on this side. Okay, on the other side, you're gonna keep having the sum over j. So at the end of the day, we got the following thing. We got that for all j equals 1 to n, the polynomial coefficients must satisfy the following: Cj dot equals minus sigma I equals 1 to n, Ci Aij, where Aij is basically the dot product of x1 phi I with phi j, which can be approximated with a quadrature rule, your favorite quadrature rule, whatever you like. Of course, you should just use sparse grids with the CC rule. This is it, okay? And there's one thing that is missing, and that is the initial condition for this dynamical system. This is now a dynamical system of n dimensions, okay? And that's the price you have to pay if you want to propagate uncertainty. You go from a one-dimensional dynamical system to an n-dimensional dynamical system, okay? And you need initial conditions for that. And to get the initial conditions, you look at the initial conditions of the original system, okay? And you just project them in that basis, right? So you can project y0 in the same polynomial basis and match the coefficients. So let's just do that right here. So you can take the initial condition, which is also depending on x, and in this particular case, it is just x1, x2, okay? In this particular case, it is just x2, and you do expand this in the same polynomial basis. So sigma I equals 1 to n, Ci at time 0, phi I x, okay? And from this you see that the coefficients at time 0, let's write them as Cj, are just gonna be, let me write them here. From this parenthesis, you're gonna get that the coefficients at time 0 are the dot product of x2 with phi j, which you can approximate also with a quadrature rule. K equals 1 to nq wk xk2 phi j xk. Make sense? So now you just have an n-dimensional dynamical system with n initial conditions. Fine, you can just solve that. Questions? Yes.
Can you explain again what are the WKs?
Oh, this is an integral, right? It's an integral over px dx. So you just go and pick a quadrature rule that integrates, that approximates this integral. This wk is the weight of this quadrature rule, and the xk's are the nodes of that quadrature rule.
The way that I'm going to pick that quadrature, will it have to have a physical meaning for my problem?
It is a quadrature rule. Okay, so let's clarify that, where wk xk k equals 1 to nq is a quadrature rule for this type of integrals. Okay, which you construct with whatever we said before. So you can, for example, get a sparse grid quadrature rule that integrates the uniform distribution and transform it to integrate this distribution. Or as I show you in the handout, there is a way, if this is a normal distribution, to get a quadrature rule that integrates a sparse grid quadrature rule that integrates the normal. You can also do that. Okay? So far, imagine we spend one lecture on these guys. We spend one lecture on the quadrature rules just to be able to do this. Okay? So the take-home message is, you take your original equation, whatever that is, a dynamical system, for example, you expand the solution on a polynomial basis, you plug that expansion inside your dynamical system, and then you get an equation that involves the polynomial coefficients, and then you start taking inner products to, reveal a nice equation like that, which you then have to solve. Now, exactly the same thing, you can do it with another model. So as we did it for a dynamical system, and we're going to do it again once more, okay? So don't worry about it. You'll see it once more. But you can also do it with a partial differential equation. So you can take the solution of the partial differential equation, expand it in a polynomial basis, plug the expansion back in the differential equation, and then get a series of differential equations for the coefficients. Okay? And you can also plug it into anything you like and derive intrusive uncertainty propagation methods for your problem. Now, why is this important? Well, here's why it is important. Here's what we have achieved. I think I need one more empty space. Once you have this polynomial expansion, so you have derived this polynomial expansion by solving an n-dimensional dynamical system, okay, instead of the one-dimensional one. What is the mean of the dynamical system? You remember? Just the first coefficient. So the first coefficient gives you the mean, okay? Because the first orthogonal polynomial is just a constant orthogonal polynomial. So when you take this expectation, is basically as if you take the inner product of y with the constant orthogonal polynomial, and this is going to spit out C1. What about the variance? Yes. So the variance is just the sum of all the polynomials except the first one squared. This is the variance. Okay? But you can also just use the expansion as to evaluate your solution at any x you like. Right? So you can just pick an x, plug it in there, and see what the solution is. Alright? Now, why is this better than Monte Carlo? Well, it is better than Monte Carlo if n is smaller than the number of Monte Carlo samples, okay, that you take. So for example, if you use 20 N's, then chances are that 20 Monte Carlo samples are not going to be enough to estimate the expectation, so you're going to do better, right? But the higher the dimension of X, the bigger the N should be, and in really high dimensional, for really high dimensional X's, the number of polynomials you're going to have to use is going to be so huge that you cannot really do that. Okay, but if you have an X that is, let's say, 2, 3, 4, 5, maybe 10 dimensions, and you expand it in a polynomial basis of, let's say, degree 2 or 3, then N is going to be smaller than the number of Monte Carlo samples, like smaller than 10,000 or 100,000. Okay? Anyway, and here's how the solution looks like, for example, when I do it for degree 1 polynomials. So I just use the constant polynomial and a line, okay, for the expansions. And I compare it to Lightning Hypercube estimate of the same quantities. This line right here compares the means, and this line compares the variances. Well, it's quite easy to approximate the mean in this case, okay? Actually, it is trivial. You just the linear expansion is enough to get the right mean. But the variance requires a higher order term. And if you go to order 2, you get it good enough, but there's still, a little bit of discrepancy there, which you're gonna have to go to order 3 or higher to correct it. And in general, this is how you make sure that your solution has converged. You start with a small polynomial degree, you increase it until the solution doesn't change. And because the mean is actually captured quite easily, you should probably be looking at the variance. Okay, because the variance is harder to capture. So if you capture the variance, chances are that you're doing a pretty good job. And the reason that it is sufficient to look at consecutive approximations is because everything is living inside a Hilbert space where everything that looks like it converges does actually converge to a point in the space. Okay, so that's the magic of a Hilbert space. Because if it wasn't a Hilbert space, maybe, this happened and things came closer together, but they didn't actually converge. Anyway. And of course, you can, once you build that expansion, you can do things like get 95% intervals, right? So you could do, for example, the mean plus or minus 2 standard deviations, or if this thing is not symmetric, you could just take samples from your expansion, so you don't have to really evaluate the model again. And take the 2.5 and the 97.5% quantiles and so on and so forth. You can, here's samples by just without evaluating the model, just using your expansion and so on and so forth. All right. Now that we did that, let's do it again. All right. Let's do it once more for another problem. It's basically very similar. Okay. You can do it for a generic dynamical system, but I think, that it's actually a little bit strange to just do it for something in that ridiculous generality. So here I'm just taking an harmonic oscillator. All right? So you have here y could be the displacement of a spring. Omega is the natural frequency of the spring. Okay? So this thing, if you displace it a little bit, it's going to be going like that. And the only problem is that the natural frequency is uncertain. You are uncertain about what the natural frequency is. Perhaps because this spring is made out of a manufacturing process that gives you a slightly different spring constant every single time, right? Or a spring with a slightly, the spring is attached to a mass that may vary depending on how you manufacture it or whatever. So you are uncertain about the natural frequency, and you are uncertain about the initial condition. Okay, so you don't know exactly where the harmonic oscillator starts, and you are uncertain about the initial velocity. That's pretty much it. Now this uncertainty, okay, is described in any way it is described, it doesn't really matter. It is just a function, the way we describe it is that x is a random variable with a known PDF, okay, and then omega and y naught and v naught are just functions of that x. So for example, right, so I can take that x to be three random numbers, x1, x2, x3, all of them standard normal, right, all of them standard normal, and I can for example say that omega x is just some natural frequency plus, a little bit of noise, x1, right? So that the natural frequency that you actually have is basically has this nominal value plus a little bit of Gaussian perturbation. We don't know exactly what it is, but so the perturbation is Gaussian. And you can do the same thing, for example, for the initial condition. You can say that it is a nominal initial condition plus a little bit of Gaussian noise, x2, and that if you want to look at the initial velocity, you can also say that it is some initial velocity, nominal initial velocity, plus a little bit of Gaussian noise. Okay? It's like, for example, this sigma 1 could be 10 to the minus 2, for example. Right? So that will give you like 1% noise or even smaller than that. All right, but this is just the modeling choice. So this garbage in here, garbage out of the way whenever you solve the problem. All right, so this requires thinking. What does this uncertainty represent in my problem? Does it represent manufacturing uncertainty of the spring? Does it represent, I don't really know, what is the mass attached to the spring? Whatever it is, that's how you think about it. But let's say that you have made this choice. It doesn't have to be this choice, just is a choice, okay? I'm gonna make this choice for solving the problem. It could be anything. The only complicating thing here is that you have a second order differential equation. Right, so before we had a first order differential equation, now we have a second order differential equation. Fine, it's not a big deal, but you need to know this trick. You need to know the trick that can allow you to take a differential equation of any order you like, second, third, fourth, fifth, whatever order, and turn this thing into a first order dynamical system. You know this trick? You do? Not linear necessarily, but a dynamical system of first order. Okay? So here's the trick. You define a set of variables. So you say, I have a second order differential equation. Let me now define a dynamical system with two variables. Well, the first variable, y1, is going to be, y1 is just going to be my original y. Okay? And then y2 is going to be the derivative of of y1. Okay? That's a trick. So using this, for example, right, you can now take the derivative of y. If you take the derivative of y1, you're going to get y2, big deal. And if you take the derivative of y2, you're going to get y double dot, which is going to be minus omega square of x y1. So it gives you now this dynamical system, the solution of which is equivalent to the second order differential equation. It's just that the first component is going to give you y, the second component is going to give you y dot. But it is a second order dynamical system, so you need two initial conditions, right? One initial condition for y1 and an initial condition for y2, and here they are. Okay? Alright, so now let's propagate uncertainties through this. Are you ready? Good. So, the first step is to construct orthogonal polynomials with respect to whatever the probability density of x is, and let's call them phi1 x, phi n x. Okay? And now let's do the following thing. Let's take 2. Let's construct a quadrature rule for integrals of the form f of x px dx, and let's call this quadrature rule wk xk k equals 1 to nq, for example, sparse grid level L, using the CC rule at the beginning or whatever, okay, whatever quadrature rule integrates these integrals. All right. Now the third thing is project in the polynomial basis everything that can be projected. Okay? So for example, let's take omega x. Let's project omega x. Here we go. Sum I equals 1 to n omega I phi I of x. We projected it. Okay? What are the coefficients? Well, the coefficients are the dot product or the inner product of omega x with the phi i's, which is approximately, using the quadrature rule, summation over the nodes of omega evaluated at the node times phi I evaluated at the node. Fine? What else do we have? Let's see. We have omega. We got rid of it. Let's project this. And let's also project this. So we project the initial condition, I equals 1 to n, y0i, phi I x, and of course y0i has to be the integral of y0 of y naught with respect with the inner product of y naught with phi I, and this can be approximated with your quadrature rule nq omega y naught xk, I forgot the wk here, phi I xk, and you can do the same thing for the velocity. Yes, I am going to write it if you were wondering about it. VOI, inner product of VO with phi I, it's the same thing. It's the same thing. Approximately sum k equals 1 to nq, wk, VO xk, phi I xk. Fine, I projected everything. Okay? Well, there's one more thing that I need to project, and that is the solution to the dynamical system. Okay? So including the solution to the dynamical system. The solution to the dynamical system has two components. This is one, y1, okay? So y1 of t, when all the random variables are x, is expanded, okay, in that basis. So I'm going to have a c1i here, and that c1i is a function of t. And I do the same thing for y2 tx. I also expand it in that basis. So it's gonna be c2i t phi I x. Okay, but now notice that this thing. So previously, all these coefficients, I could find them because I know these functions. So all I have to do is the integration. But now these coefficients, I don't know them. Okay, I do not know them. But what was that? Because I have to solve the dynamical system to know them. Right? That's why I don't know them. But I'm saying, let me expand the solution. Now I'm going to take these expansions and I'm going to plug them in there. Okay? And now I'm going to have polynomial expansions everywhere. And I'm going to match the coefficients. Okay? So let's just do this. So let's call Let's call this 1, this 2, this 3, and this 4, and let's just project the hell out of it. So here we go, we take 1, and we just plug in this expression, right? So we're gonna get that y1 dot equals y2. This is gonna give us sum I c1 I dot phi I of x equals sigma I c2 I phi I of x, from which, of course, you just compare the coefficients of the polynomials are orthogonal, so the coefficients must be equal. So you're gonna get that c1i dot equals c2i. Fine, okay, that's one differential equation that must hold. Now, if you do that for equation number 2, you're gonna get y2 dot equals minus omega squared x y1. Okay, this is a little bit trickier. Now you have sigma I c2i dot phi I of x, and now you have an expansion for omega. You have already done that, so it's going to be sigma. Let me use another dummy index for omega. Omega j phi j of x squared. Fine, and here I have sum I c1i phi I x, and it looks like that. Okay, it just looks like that. And now you can actually do this summation. You're gonna get a triple summation, okay, out of that. I don't know if you can see it right away, but you're gonna get minus sigma I j, pick your favorite letter, r, okay? And we're gonna have omega I, omega j, phi I of x, phi j of x, and then we're gonna have here the c1k, phi k of x. Sorry, I called it r. c1r, phi r of x. Fine, I can rearrange it a little bit, make it a little bit more beautiful. So let me just write it like that. Sigma I j r, omega j, c1r, phi I x, phi j x, phi r x. And now I have that this must be equal to that. They're both functions of x, and I need to get an equation for the coefficients. And the way I do it is by taking the dot product with another polynomial. Okay, but you're gonna have to pick another index for that polynomial. I don't know, call it s. Okay? So now you take the dot product with phi s. Okay, of both sides of the equation. And this is gonna give you from this guy, it's just gonna give you C2s dot, this is what it's going to give you, and on the other side, right, it's going to give you minus sigma I j r, it doesn't go anywhere, omega I, omega j, c1r, these are all constants, and then you have the inner product of phi I, phi j, phi r with phi s. Okay? And this is an integral, whatever. And you can use a quadrature rule to approximate it. Okay, wk, whatever. And at the end of the day, now you have a differential, a dynamical system that has 2n components. And of course, you need to do this as well to get 2n initial conditions. And then you put everything together and you solve them. And this is what is in the handout. Okay, so I did this in the handout. Trust me, it takes about a day to get it right. If you have done it again in the past. If you do it for the first time, I don't know. but it takes about a day to program it right, okay, because it's a little bit tricky. But anyway, so this is on your handout, and you can see that you can actually do this with the code that we have seen so far. And now I just solved the problem for this particular uncertainty. So I'm saying that the natural frequency is 2 pi plus some noise that is actually quite big, okay, has variance 1. And I'm taking the initial condition to be 1 plus a little bit of noise, and the initial velocity to be 0 plus a little bit of noise. Okay? And this is how the expectation, this is the basically the predictive error bars for the position of the oscillator. So the blue line is the expectation, and the shaded area is 95% predictive interval around the expectation. So you see, how it goes, and that the uncertainty grows as time goes by. And this is the predictive interval for the velocity. Okay, as this happens, it's actually less, the velocity is less uncertain. And this is pretty much it for that. Okay, are you ready for the final part, which is how you can do that without really doing all the math? Okay, so far we've seen the methods that we've seen. The method that we've seen is called intrusive polynomial chaos, because you actually have to sit down and come up with a dynamical system that replaces your original system, but the solution of which propagates uncertainties. All right, so let's say that you're too bored to do that, okay, or that you have a problem that has a solver that you cannot really mess with, okay. So let's say that you have a model that has been developed for 10 years and you just have a Fortran code that you don't really know what it does, you just want to use it.
What happens if the output is multidimensional?
So you do that for every dimension.
So it doesn't, you don't need to, your dimensionality is the same. You just repeat it for every...
Yeah, you repeat it for every... So here, if you look carefully here, I actually have a 2-dimensional output at every time step. So in reality, you have a very high dimensional output. You just expand every output you have in the same basis. Okay, you're gonna get as many coefficients as your outputs. But anyway, so here's how you can do that now without really messing with your solver. It's actually ridiculously easy to do it. It's so easy that I can't think of a way why you would like to do intrusive polynomial chaos. Honestly, I can't think of a way. But here it is, okay? It's very straightforward. So you have your dynamical system. Now it's so straightforward that I don't even have to give you a specific example. I can just do it with a generic one. So say a generic dynamical system, dy dt equals g yx. If you're careful enough, if you pay attention to what I'm saying, it doesn't even have to be a dynamical system to do this thing. It can be any function of x. Okay, so you have initial conditions, and you have this x being uncertain, has a probability density p of x. I should have used a capital letter here. Big deal. So the idea is that you expand the solution of your dynamical system in the polynomial basis, just like before. The coefficients are going to be function of time, all right? But now, instead of plugging this inside your dynamical system and writing a new code, you say, let me just take the dot product with phi, because I know that the dot product with phi is going to give me the coefficient ci. Okay, so I take the dot product with phi, fine. It is this integral, fine. Let me just use a quadrature rule and approximate it. So what does that require? It requires you to solve your dynamical system with your regular dynamical system solver at the quadrature point. Okay? Now, admittedly, the other thing that it requires you to write a solver from scratch may actually work better, okay, in the sense that if you pay the price of writing the solver, it will work faster than this. But if it's gonna take you like a month to write the solver, then you just wait for, just run your original model for a month and maybe that will accomplish the same result. Okay? So whenever you solve an uncertainty propagation problem, or whenever you're solving an engineering problem that has a significant cost for information acquisition, you doing experiments or evaluating expensive models, then you should take into account, when you select the solution method, how much time it actually takes for you to develop the methodology. If that is more than half the time of the PhD, for example, maybe, just maybe, you should do something else. Okay? And it depends. If your PhD is about developing the methodology, then fine, do it. But if your PhD is about solving a problem, then don't feel restricted by the method. Right? Just take into account the amount of time it takes to learn something and implement it when you're selecting what to do. Anyway, this is it, and it gives actually exactly the same result. Okay? So, but now you have to make two choices. So you had to make two choices before, but I didn't really tell you about it. So you can pick the polynomial degree of your expansion, and you can also pick the level of the sparse grid that you're using. So here I'm showing you the result with polynomial degree 3 and sparse grid level 1, which has 5 quadrature points. So it just requires it's sparse grid level 1 in three dimensions. And I'm not even sure that it's level 1, but anyway, let's just say that it is L level. It has 5 quadrature points. I'm sure about that. And just five evaluations of the model gives you basically a perfect mean, but the uncertainty is not perfect. So you decide to increase the level of the sparse grid quadrature. You see that sparse grid quadrature level 2, you get a perfect match for the uncertainty. And sparse grid level 2 in 3 dimensions corresponds to 21 quadrature points. So just 21 evaluations of your model. Okay? So even if your model takes like a week to give you a single evaluation, this is 21 weeks. Perhaps if you can do it in parallel, it's going to be 1 week. Right? How much time does it take you to write the solver from scratch? Maybe more. I mean, it never works the first time. Anyway, and then you get to make sure that it is right, you have to go to higher quadrature, because here we know the solution, but whenever you're solving a new problem, you don't really know the solution. So you're going to have to increase the polynomial degree and increase the sparse grid level until things do not change. All right, now we have 15 minutes, and the plan is for you to just run the code that does that. Now I know that you really want to do the homework, so feel free to do the homework, okay? But let's keep in mind that the handout is out there, okay? You can do the handout. I will be walking around helping you with the handout if you want. The handout is out there. We're going to have a homework problem in which, a homework set in which you're going to have to propagate uncertainties with polynomial chaos, okay? After polynomial chaos, we're going to start Markov chain Monte Carlo, and we'll see how we can solve inverse problems finally.